Okay, so today we're going to be doing an introduction to vectors in a plane. And so what a vector is something that has two-dimensional motion. It has both magnitude and direction. So you can see here they talk about the magnitude, it's just its length, and the direction would be the way that it's pointing. So, for instance, if I told you I was going 70 miles an hour, that's what we call a scalar quantity. I only know one thing. I know the magnitude at which I was traveling. This is going to be 70 miles per hour north, or 70 miles per hour 20 degrees north of east. Okay, we have to give magnitude, which is the 70, and we have to give the direction that it's traveling. So, like I said, I kind of covered this. You can see that we use a ray to represent a vector. So they call it ray PQ, where P is the initial side. That's where we begin. Q is the terminal side. So that's where we're going to end.
Excuse me, teachers, I have one more that I forgot to do. The lunchroom is serving pizza and corn today. Today's menu has changed. It will be pizza and corn, and I understand it's going to be on paper plates. Thank you.
Okay. Now, the way that we talk about magnitude is just the length, or in other words, it's the distance from P to Q. But with vectors, the way that we show length or magnitude is we use this notation here. You see the double bars? It almost looks like two absolute value bars on each side. So if you see this question, double bar, PQ, double bar, this is the magnitude of PQ. And the way we find that is by using the distance formula. So when we look at all of these rays, so do they all look the same? Well, they look like they start in different places. But it turns out their magnitude, which would be the length of the ray, and the direction that they're facing are all the same. So if they have the same magnitude and the same direction, they are the same vector. They are equivalent vectors. So two directed line segments that have the same magnitude and direction are called equivalent. For example, the directed line segments in figure 6.12 are all equivalent. The set of all directed line segments that are equivalent to a given directed line segment is a vector V in the plane. And so a lot of times we use V, U, and W to talk about vectors. So you can see they said V was equal to ray PQ, and then we're going to just refer to that vector as V from now on. So right here the question is, they want to know, are vectors U and V in the figure on the right equivalent? So you can see how they've named them. This is vector V, this is vector U. So the first thing, for them to have the same, or for them to be equivalent, we must check two things. We have to find out, are their magnitudes the same? And is their direction the same? So again, magnitude, that's just the distance of the vector. So we're going to start by finding the magnitude of U. So again, we put those two absolute value bars on each side. So how do we find magnitude? Well, we just use the distance formula. So in case you've forgotten, distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So when I'm looking at vector U, it's very nice. Why? Because one of my points is the origin. That makes life very easy for me. So now I do the square root of 3 minus 0 squared, which is just going to be 3 squared, plus 2 minus 0 squared, which is just going to be 2 squared. Now when I simplify that out, that's going to be the square root of 9 plus 4, which is radical 13. Right, now I need to check, does the magnitude of V match that? So now here for the magnitude of V, this time my distance formula is going to be a little bit more tricky because one of the points is not the origin. So if I go x2, I'm going to call that 4, minus x1 squared, plus y2, 4 minus y1 squared. If I simplify that, which again, I know y'all can put that right in your calculator. If I simplify that, that's going to be 3 squared plus 2 squared, which is radical 13. So do the two vectors have the same magnitude? Yes, they do. They both are radical 13. So that means they have a chance to be equivalent. I just need to check, do they have the same direction? Okay, so the way we check direction, if it's already graphed for us, it's pretty easy. We can just look at the slope of the lines. If the slopes are the same, that means they're in the same direction. They're parallel. So let's find the slopes here. So the slope formula, in case you've forgotten, is y2 minus y1 over x2 minus x1. So first, let's find the direction of u. So the slope of u would be 2 minus 0, which is 2, over 3 minus 0, which is 3. So the slope of u is 2/3. Now let's find the slope of v. That's going to be y2, 4, minus y1, 2, over x2, 4, minus x1, 1. That's going to give me 2 over 3. Do these have the same direction? Yes. So because they have the same magnitude and the same direction, they are equivalent vectors. Okay, so hopefully you've been working this out. You found the magnitude of u to be radical 10. The magnitude of v is also radical 10. The slope of u is 1/3, and the slope of v is 1/3. Don't need to go over any part of that. Slope of u. Magnitude of u. Of u or v? Both? Okay, so magnitude is just the distance. So we're going to use the distance formula. So the magnitude of u is going to be the square root of. So I'm going to treat this as my x2, x1, and 0, 0 is going to be my x1. I'm an idiot. This is going to be my x2, y2, and 0, 0 is going to be my x1, y1. So if I plug into the distance formula, x2 is 3 minus x1, 0 squared, plus y2, y2, 1 minus y1, 0 squared. So that's just going to be 3 squared plus 1 squared. Or when you have zeros, when you have the origin as a point, that makes it very easy. And so 3 squared is 9, 1 squared is 1, 9 and 1 is 10.
What about the slope of u?
Let me do magnitude first. So magnitude of v, that's the square root of. So same deal, y2. This time I'm going to use 3 minus y1, 2 squared, plus x2. So this time I'm flipping it around. It doesn't really matter. 5 minus 2 squared. Because you're adding them, you just have to subtract the x's, subtract the y's, square them, and then add that together. So I did out of order. It's my fault, but it doesn't really matter. That's going to be 1 squared plus 3 squared, which is still radical 10. Any other questions on magnitudes? Okay, slopes. We just use the slope formula. y2 minus y1 over x2 minus x1. And so you said the slope of u.
Mhm.
So I'm going to use these same. This is still my y2, x2, y1, x1. So if I plug in, it's going to be y2, which is 1, minus y1, 0, over x2, 3, minus x1, 0. 1 minus 0 is 0. 3 minus 0 is 3. It's 1/3. Another way you can do it without the slope formula, if you have the graph, remember slope is just rise over run. So if I'm going from here to here, I rise 1, I run 1, 2, 3. So that's 1 over 3, which is 1/3. You can do the same thing here. I rise 1, I run 1, 2, 3. So that's just another way you can do slope. It might be easier if y'all had your books. Y'all probably didn't bring them because you hadn't used your books all semester. But we're back using the books till the end of the year. We're done with the trig stuff. Is often the most convenient representative of a set of equivalent directed line segments. So what they're saying is when one of your points is the origin, it makes our life easier. Right? I mean, that's what they're saying there. When we have one point start at the origin, we call this vector being in the standard position. A vector whose initial point is the origin can be uniquely represented by the coordinates of its terminal point, which would be at v1, v2. This is the component form of a vector v and is written as v equals. So you can see here, instead of using parentheses, they use, it looks like sideways V's, right? Like almost a less than sign and a greater than sign inside there. What this tells me is I have a vector that starts at the origin and it ends at, this is the x value that it ends, this is the y value that it ends. Okay, so that's your standard component form of a vector. It tells me my x component and my y component. The coordinates v1 and v2 are called the components of v. If both the initial point and terminal point lie at the origin, then v is a zero vector, and it's denoted by 0, 0. So we're not going to deal with that much, but if I have a vector that goes nowhere, points nowhere, then it's going to start at the origin and end at the origin. Well, that's, again, just a zero vector. All right, let's keep looking. I think that says nothing. Yeah, I'm not worried about that right now. Two vectors, u and v, are equal if and only if the x components are equal and the y components are equal. For instance, in example 1, what did I do? There we go. In example 1, the vector u from 0, 0 to 3, 2 could be written as 3 minus 0, 2 minus 0, which is still 3, 2. Right? Because one of the points was the origin, it made it very easy. Now, if I wanted to write the component form of this vector, that's a little bit trickier because one of the points is not the origin. So if I want to find where the x is, what's the x component? We would just do 4 minus 1 to find that x component. And then we would do 4 minus 2 to find the y component. And we could see that they have the same component form, which means they are the same vector. So again, we're just proving the two vectors are equal in a different way. After I showed you magnitude and direction, now we're just comparing their component forms. So it tells me to find the component form and the magnitude of a vector v that's represented by a directed line segment that starts at 4, negative 7, and it ends at negative 1, 5. Okay. So if I just think about it, if I'm at 4, negative 7, I'm just making myself a little rough draft here. Here is my initial point, and it ends at negative 1, 5. So it's going to go this direction. So when I find my component form, it needs to be somewhere in the second quadrant, right? Because once I move it to the origin, I expect it to go in that direction. So just kind of in my head, all right, if I don't get the second quadrant, I'm wrong. So if it starts here and it ends here, we start with the endpoints. So let's start with the x's. The end x is -1. We're going to subtract the beginning x, which is 4. And I completely messed up where that goes, didn't I? And y'all are not going to say anything to me. If I'm at -1, 5, I'm not even close. Y'all didn't say anything to me. I don't appreciate that. This is my vector. That's going to be much larger in scale. Now, what I said was true. It's still going to start at the origin, and it's going to be in the second quadrant. But my numbers would have been crazy off. So anyways, how do we find the component form? We subtract the x's, where it ended minus where it began. And then we're going to subtract the y's, where it ended, 5, minus where it began, -7. So this would be -5, 12 is my component form, which again is going to the left and up. So left 5, up 12. Something like that. I've just moved the vector to make it start at the origin. I put it in standard position. All right, so I found the component form. That's the first part of the question. What's the second part of the question? Find the magnitude. Magnitude is just the distance. So we can find the magnitude of V. So when it's in its component form, it's really easy because I know one of the points is going to be 0, the origin. So I could take the x value squared plus the y value squared. That's going to be radical 25 plus 144, which is radical 169, which is 13. So I knew that from the get-go because I know my Pythagorean triples. This is a 5, 12, 13 Pythagorean triple. Y'all remember those? Like 3, 4, 5, 5, 12, 13. So I didn't actually have to use the distance formula. My original vector was here from the red to the red. And now when I find the component form, I'm taking that yellow vector and I'm moving this initial side to the origin. And it should be the blue vector now. And so hopefully you found the component form of V. You're going to take where it ended, the x that it ended, and subtract the x that it started at. So -7 minus -2. Then you're going to take the y that it ended at and subtract the y that it started at. So that should be -5, 6 is your component form of your vector. And then to find the magnitude of V, we're going to plug these component forms into the distance formula. So it's going to be x squared plus y squared, which gives us radical 61. So first thing, I told you a vector had two things. It has magnitude and it has direction. The way that it is pointing matters. And then I told you that speed, like 70 miles an hour on its own, that has no direction. That has only a magnitude. Well, only having a magnitude, we call that value a scalar. I don't know if I said that earlier or not. I don't think I did. But a scalar is something that has no direction. It has only magnitude. So we can multiply a vector by a scalar. And that is called scalar multiplication. So here's an example. If I have a vector V, see how this vector has a magnitude and it has a direction. If I were to multiply this vector by scalar, such as 1/2, then I did not change the direction of v, only changed the magnitude of v. Now v is half the size that it was before, but it's still facing the same way. If I were to take v and multiply it by a scalar 2, look what happened here. This vector has the same direction, but now it's twice as long. I've changed its magnitude, but I didn't change its direction. What happened to this vector? It got multiplied by -1. So what happened there? We changed the start and the end, the initial side and the terminal side. Instead of the vector going in this direction, it's now going in the exact opposite direction. It has the same magnitude. Think about it like a reflection, right? When you put a negative out in front, you're reflecting it. It's going in the opposite direction now. And then right here we multiplied v by, this is -3/2. I know that's hard to see. So -3/2, that's a little bit more than 1, right? That's 1.5. So it got stretched, but now it's still facing in the opposite direction as vector v was before. So again, those are scalar multiplications. The other thing we can do is we can do vector addition that we're going to talk about. So if we add two vectors, if you think about it graphically, we're going to line the vectors up nose to tail. So if we do u, so tell me to do u plus v. I'm going to take vector u, and it's going to stay where it was. So right here is vector u. It's in its same position. But now if I'm going to add v to it, I'm going to take the tail of v and put it on the arrow of u. And so now this vector v lines up here. And if I do u plus v, that's going to go in this direction. This is my final product. How I've added u and v together to get this new vector. You can notice they've kind of dotted the line for me. What do you think this dotted line represents? This dotted line would be if I did v plus u. Did I get the same answer? I did. So u plus v and v plus u give the same answer. So it doesn't matter the order in which you add them. You'll still get the same resultant vector. And you see that's the word that they use. Resultant vector is the vector you get after you've added two of them together. That's what resultant vector means. Component forms. So that means they're centered at, or they've got a starting point at the origin. If I have u and v in their component forms, and I want to add u and v, I'm just going to add the two x's, right? u1 and v1, and then I'm going to add the two y's, u2 and v2. And that's my new resultant vector. Just add the x's, add the y's. If I want to do scalar multiplication, which is what we looked at the very beginning, where we stretched it, where we shrunk it, but it kept its same direction, we're going to take our vector, u, and we're going to multiply k by both the x component and the y component. Basically distribute. Okay, so I've got two vectors, and they give me their component form. V is at -2, 5 component form. W is 3, 4. If I've got to find each vector, first it tells me to find 2 times v. So this is a scalar multiplication. So I'm going to take 2 and multiply it by v, which means I'm going to distribute it. That's going to give me -4 and 10. So a part is the vector -4, 10. So again, if you think about that graphically, it's going to be in the same direction as it was before. Because think about -2, 5. I'll be going left and up. -2, 5. Where's -4, 10? It's left and up. It's still in the same direction. We've just stretched it to give it a greater magnitude. Okay, B part tells me to do W minus V. So this time I'm going to take my vector W, which is at 3, 4. I'm going to subtract my vector V, which is at -2, 5. Okay, you have to distribute that negative. right? So this is going to give me 3 minus negative 2 means I'm going to add 2. And 4 minus 5 will be my y components. So this is going to give me 5, negative 1. So what do you think is happening when I subtract a vector graphically? When I added a vector, I did what? I took the end and put it on the arrow of the previous vector. If I'm subtracting a vector, that's just like a negative 1, right? A scalar multiplication. So when I have my original vector, I'm going to flip the second vector and then put it on the arrow. It's going in the opposite direction of what it normally did because it's basically being multiplied by the scalar negative 1. And then the last one, I've got v plus 2w, which means I'm going to take my vector v, negative 2, 5, and I'm going to add 2 times w, which is 3, 4. So what do you guys think is going to happen here? Order of operations. So you're going to have to multiply the scalar before you add the vectors. So multiply 2 by vector w. So that's going to give me 6, 8 for 2w. Then I'm going to add that to v, which is negative 2, 5. Now we add the x's. So negative 2 and 6 gives 4. 5 and 8 gives 13. So my final vector, my resultant vector, that's the word I need to be using. My resultant vector is 4, 13. Okay, what do we get for A? It is 4, 6. Questions on A? We get on B. It's negative 2, 2 for B. Questions on B? C. Negative 7, 2. Questions there?
Okay.
Yep. So I've got 2 times U, which is at 1, 4, minus 3 times V, which is at 3, 2. So you have to multiply first before you can add or subtract. So I'm going to multiply the first vector by 2. That's going to give me 2, 8 as my resultant vector. And then the second vector, when I distribute that negative 3, that's going to give me 9, or negative 9 and negative 6. And I'm just combining. When I combine 2 and negative 9, that's negative 7. When I combine 8 and negative 6, that's positive 2. All right, next thing we're going to do, we want to find the magnitude of each scalar multiple. So what does magnitude represent? Magnitude is the distance that the vector is. Distance is always positive. Magnitude is always positive. You can't have a negative magnitude. So if you have a negative number in the end, we take the absolute value of that, because distance is always positive. So there's a couple different ways you could do these problems. When I look at A, I could multiply vector u by 2 and then find the distance. Or I could find the distance of u and then multiply it by 2. It does not matter which order you do it in. Just pick one and go with it. I think it's easier to find the distance before I do the scalar multiplication because the numbers are smaller and they're a little bit easier to work with in my head. So if I had to find the magnitude of 2u, that's the same thing as finding the magnitude of u and then multiply that number by 2. So that's what I'm going to do. So in this problem, the magnitude of u, that would be 1 squared plus 3 squared, that's 10. And then take the square root of 10. So the magnitude of u is 10 times 2, which I can write as 2 radical 10. So I know I did that all in my head. Are y'all good with how I found magnitude? No. Magnitude is the distance formula. So what's the distance? That would be the square root of 1 squared plus 3 squared. Because one of my components, one of my initial starting point is at 0. So I just do 1 squared plus 3 squared. That's how I find the magnitude of u. Does that make sense? Do you have more questions about how I found 2u? Okay, so B part, if I have to find negative 5u, the cool thing here is I already know what u is. Right? It's going to be the magnitude of u times, and this time it's going to be times negative 5. Well, I told you we can't have a negative magnitude, so we can think of that as being the absolute value of negative 5, which is positive 5. I just showed you above the magnitude of u is radical 10 times 5. That's going to be 5 radical 10. Everybody good with that? Or no? Lastly, the magnitude of 3v. So now I'm going to find the magnitude of v and then multiply that by 3. So the magnitude of v, that's going to be negative 2 squared plus 5 squared. So that's going to be radical 4 plus 25. That's radical 29 times 3. So that's going to give me 3 radical 29 for the magnitude of 3v. We're going to go ahead and give these answers. Make sure we got time. On A part, what did you guys get? Should be 3 radical 17. 3 radical 17. If you did 15, you probably subtracted 1 instead of adding 1. B part is 2 radical 13. And C part is 5 radical 13. So I've got to find the magnitude of u. It's going to be the square root of 4 squared plus negative 1 squared. That's going to be the square root of 16 and 1, which is 17, radical 17. Got the part you need to see?
Yes, thank you.